please get seated. Nem hallatszik? So please get seated. We'll start with, in a minute, with our hallatszik? We start with this second invited talk of SoCG. So it is my honor to introduce András Máthé. He's a mathematician. He represents the Hungarian School of Metric Geometry. Other prominent members of this school are Miklós Lackovics, Márton Elekes, és Tamás Keleti. This is the metric geometry is where we learn about the Kakaya problem that is related to incidences, and some of the problems that Máthé will talk about also related to incidence problems. So he has been in Warwick, University of Warwick in the last 9 years. Just last year he received the Whitehead Prize from the London School of Mathematics, and he also represents the University of Warwick at the International Congress of Mathematics in Rio later this summer. But let's hear what he has to tell us today.
Thank you very much. So, actually, when I'm in Hungary or when I'm meeting combinatorists, I always just say I'm doing geometric measure theory, which is a bit of a lie, because whenever I meet proper geometric measure theorists, I just tell them I realize that I'm doing combinatorics, which is even a bigger lie, but, well, maybe it's not so important to categorize what we do. I will present today 3 or 4 different sets of problems I'm interested in. So the first one is going to be circle squaring. To start the story somewhere, let's start with this result from the 19th century. It says that if we have 2 polygons in the plane and they have the same area, then we can dissect one into smaller polygons, even triangles, and then translate and rotate these pieces, and we obtain the another polygon. Now, Hilbert's third problem, which was actually the first problem of Hilbert which was solved, is the related question in 3 dimensions. So is the same true for polyhedra? So if we have 2 polyhedra in space of equal volume, can we always cut the first one into finitely many polyhedral pieces, and then rotate these, translate these to obtain the another polyhedra? And Hilbert's student answered this a couple of, I don't know, maybe years later that no, and he came up with an algebraic invariant which proved that this is impossible even for the cube and the tetrahedron. We will get back to this later. Now, set theory evolved a bit. Here came another similar problem, and this is the Banach-Tarski paradox. So let me show you how this works, because I actually have the hat of Banach and Tarski. So here it is. So this is the hat of Banach and Tarski, and if you take an orange and you put it into this hat, then you can actually see, or well, I can see that it cuts this orange into 5 pieces, very, very ugly pieces, and then rotates and translates these, and in the end, it obtains 2 oranges. Here they are. Okay? Okay, so I will say that 2 sets A and B are equidecomposable if this can happen with one orange is equidecomposable to 2 oranges. Of course, the pieces that the paradox uses cannot be measurable. They cannot have volume, because we increase the volume from 1 orange to 2 oranges. The Banach-Tarski paradox is a bit more general. The same works with basically any 2 bounded sets that have non-empty interior. Okay, so the proof of the Banach-Tarski paradox relies on the Hausdorff paradox. I'm not going to talk about this. You don't actually have to read the slide, but it really relies on that the rotations in space is a large group. It contains the free group on 2 generators, and once you have the free group on 2 generators, you see this nice infinite branching tree, binary, well, tree, and then paradoxes appear. So my daughter is only 6 years old, and she sort of realizes that probably I'm a teacher too, and she asked me what I'm teaching. But I didn't tell her this one. I just told her about, I don't know, in space there is a hotel with infinite rooms, and it's full, but one guest arrives. Well, so this, probably you know these kinds of problems. This is not much more complicated. Okay. So the paradox is in R3 or in higher dimensions. It doesn't work in the plane. The reason it doesn't work in the plane is that the isometric group of the plane is much smaller. It's a solvable group. Let's just look at the last piece here. So what you can prove that in the plane, if you have two sets that are equidecomposable, that implies that the two sets must have the same Lebesgue measure. So if you start with two measurable sets and you can use arbitrary pieces, non-measurable, even with those, you cannot change the area of the set from going to A to B. Okay, but there was a similar, very interesting question open already from the 1920s, Tarski circle squaring. Okay, so now I take two sets of the same area, but one of them is a disk and the other one is the square. Can you equidecompose one to the another? They should have the same area. And this was unsolved until 1990, when Miklos Lackovic, who was actually my PhD advisor, proved that they are equidecomposable, and actually he only needs translations to prove this. His result is more general. What is important, it's not important that it's a disk and a square, it's only important that their boundary behave nicely. Later I will define Minkowski dimension, perhaps. If the boundary of these sets are piecewise smooth, then that's enough. Then you can equidecompose one set into another. Okay, now the question is, what remains true from these theorems if we replace arbitrary pieces by measurable or Borel pieces? Okay, so you cannot use this hat, which can divide pieces into non-measurable sets. You can only divide the set into measurable sets or only Borel sets. Now, with Lukács Grabowski and Oleg Pikurko, we realized that some clever work of some clever people can be combined into proving the following theorem. Basically, Banach-Tarski paradox works with measurable pieces, well, with the obvious assumption, unfortunately, of course, that the two sets should have the same measure. So if we have two bounded measurable sets, same measure, non-empty interior, then equidecomposable using measurable pieces. So although Hilbert's problem cannot be solved with polyhedra, but you can divide the cube into finitely many measurable sets, rotate them, translate them, and you get the tetrahedron. Or you can also get the ball of the same volume. Now, what about the circle squaring result? So I'm mentioning two different problems here. So this one worked in space, so it's important, it's in space. What happens if we are still on the plane, the disk and the square? We managed to prove by looking into Lackovic's proof, that actually this circle squaring is possible with measurable pieces. And we also have to use only translations, no rotations. Not much later, I'm not sure whether it was weeks or months, Marx and Unger proved the stronger results that it works with Borel pieces too. Now, of course, this is the place when I should include a picture, right? Now I'm using measurable sets. Measurable sets can sort of be drawn. It's possible. But you won't see a picture on animation for the reason that even Lackovic's proof, his estimate is that he needs about 10 to the 40 pieces. So it would be hard to visualize 10 to the 40 pieces on this screen. We need at least that much, maybe a bit more. At least that's what the proof gives. Okay, some more pictures anyway. So how to look for these equidecompositions? So a standard technique would be that you divide the set into pieces somehow, and then you're trying hard to reassemble to yield the another one. Okay, so if you look carefully, you could see that this didn't work. It's actually not the same pieces, not exactly. So the right way to find equidecompositions is, in some sense, the other one. So you first fix some isometries or translations, the ones which one want to use, and then somehow you take even more and then try to find the partitions that work. So first fix the rotations, the isometries, and then find the partitions. And let me try to explain why this is connected to graph theory. So let's fix some isometries, finitely many, of course. And we are trying to find equidecomposition between two sets, maybe a cube and the ball in R3. Let's consider the bipartite graph that contains that the vertices is A union B, I mean the two sets of vertices A and B, and there is an edge between a point little a and little b if you can find, if one of your isometries moves A to B. Okay, this is the obvious graph you can define. Of course, this graph has continuum many vertices, but it's a nice graph because rotations are nice, smooth maps. And the claim is that there exists a perfect matching in this graph G if and only if A is equidecomposable to B using exactly these isometries. And the proof is usually more complicated than what I can understand when I'm talking, but it's very simple. So perfect matching, of course, is just a bijection from A to B that always uses an edge, and if you have a bijection, then you can define the partitions. The set AI should be just those points in A for which your bijection uses the isometry gamma I. And that works, so it's a totally straightforward claim. Okay, so and now here is our result again that you can. It's a measurable version of Banach Tarski. I will tell you something about this proof. It has the special case, which is technically the easiest, is if instead of the space we are just on some nice compact set. So let's stay on the sphere, maybe the two-dimensional sphere or the d-1 dimensional sphere. And here we are trying to prove that if you take two measurable sets of equal area or measure, and they have non-empty interior, then they are equidecomposable using measurable pieces. Equidecomposable now means that you can only use rotations of the sphere. And what do we need? So Banach-Tarski paradox relied on having a free group in the isometry group, and our result is measurable. We need just an analytic or quantitative version of this statement. And a clever result of clever people, and the first one is that you can define an average. If you have, so there you can find finitely many rotations in SOD, such that this averaging operator here that you can see here has a spectral gap. Spectral gap means, okay, of course, this averaging operator preserves the integral of measurable functions. So there is one eigenvalue of 1, but otherwise, from that, all the others, I mean, all the spectrum is below 1 minus epsilon. It doesn't important that you actually understand it, but it means it's actually equivalent to the following expansion property, which now really talks about graphs and how things behave on let's say, the sphere. So it means that you can find finitely many rotations, such that if you take any either finite set X or any measurable set X, and you look at, I take the union of all the images, then its measure, lambda just stands for my surface, Lebesgue measure on the sphere, then its measure is some constant, maybe at least 2 times as much as the original measure of X. This actually says it's 1 over delta times as much as the original measure. Just replace that with 2. Of course, it cannot be more than 1, so there's this technical thing that it's at most 1 minus delta. But now, so this is what we know on the sphere, and this is nothing like that is true on the plane. And of course, you also have to take into consideration the graphs you have. But even if you have these sets A and B of non-empty interior, you can prove a similar expansion property inside the graph G. I'm not going to explain what it means. There's the formula. So somehow, it still means that sets increase with exponential rate in the graph G. And there's another clever result by clever people, Lyons and Nazarov. They proved actually that those graphs that have this expansion property actually have a Borel perfect matching up to a null set. We don't have to bother about null sets here. And the reason is that this expansion property implies that you can find short augmenting paths. Maybe I'll try and explain that bit a little bit. So, bipartite graph, we are looking for a matching. If the graph is finite, what happens? I'm just using this algorithm of starting with the empty matching and then find an augmenting path, increase the matching, find an augmenting path, increase the matching, and so on. It's a nice algorithm. For me, nice algorithm means it finishes in finite time. That's where my, I'm not a combinatorist or computer scientist. So it finishes in finite time, that's enough. And we get the largest possible matching that one can get. If it works, then it's a perfect matching. Now, what happens if we try and do the same for a Borel graph on continuum many vertices? Actually, the same is possible to do. I think this maybe goes back to an idea of Alec and Lipner. Instead of just finding one augmenting path, you look for a family of disjoint augmenting paths. It looks like the picture. So somehow it positive measure. The vertices that you move or change, it has positive measure. And then you do the same thing. You find augmenting paths to change the matching. Only problem here now, this algorithm might not finish in finite. Usually it won't finish in finite time. It takes an infinite steps. And it might or might not converge to an actual matching. So that's what you have to check in an actual case, that it converges to an actual matching. And what Lyons and Nazarov's expansion property implies that because somehow there are short augmenting paths, it converges. Okay. So now let's go back to the circle squaring. So what are the results about the circle squaring? Lotskowicz proved that you can do it enough to use translations, and then Marx and Unger proved that actually the pieces can be Borel. Now, I would like to tell something about the proof of this. Well, probably I will only get into Lotskowicz's proof and nothing else. Okay, maybe I have 20 seconds for negative results. So Borel pieces are not true. It was known already from the 60s that the pieces cannot be too nice. So they cannot be Caesar congruent, which means something like they are Jordan domains, and you can forget about the boundary of the domain. And it was also known that the translations you use or the group you use have to be large in a sense. It cannot be a locally discrete group. Okay, now, Lotskowicz's proof. Let's try and understand how it goes back to a graph and perfect matchings. I know we are in the plane, but everything is much nicer if we just pretend that we are not torus. We can pretend that. So now A and B are nice subsets, maybe a small disk and a small square inside the torus. And then Lotskowicz chooses, actually, random way, many translation vectors. It says D. D has to be large, depending on the sets you have. Okay. Now, the actual translations you would like to use in the equidecomposition will be a small integer linear combinations of these vectors you have already picked, of the random vectors you picked. Okay. Okay, let's build up the bipartite graph we are interested in. So the vertices are again A and B points on the torus, and something is an edge if you can move from A to B by a translation in this set gamma C. Same setting. Okay, so it's a graph with continuum many points, but still the degree everywhere is finite. So, now, just as before, an equidecomposition of A and B using translations. These translations is the same as the existence of a perfect matching in this graph GC. So that's what we have to work on, proving that there exists a perfect matching in this nice graph. Now, if we assume the axiom of choice, and we assume the axiom of choice, this is the same as just as proving that in every connected component, there are continuum many connected components, there is a perfect matching. Okay, and Lotskowicz will check that actually this is true. Indeed, in every connected component there is a perfect matching, but gluing them together, that's a difficult job. You cannot necessarily do it in a measurable way. So all these Borel and measurable versions of the same statement has to do something else and not just work in connected components. Okay, I just identified 2 steps in the proof of Lackovich. Step 1 is, so these sets A and B are quite nice on the torus. That somehow implies that in this connected component we know much more than what would just ergodic theory would tell you. Actually, if you use discrepancy theory, something like the Erdős-Turán-Koxma inequality, that implies, that gives something nice for the structure of the graph in every connected component. And this Erdős-Turán-Koxma inequality is just a generalization of an inequality which is so standard in Hungary that it was included in my first Fourier analysis course by Gábor Halász. Okay, so what do I mean by understanding the structure of the graph? It means that it's enough to solve the following discrete problem. So the hard work Lackovich has to do is actually solving this discrete problem here, and that's step 2, proving this. Okay, so what's the setting? We have this integer that is ZD, I mean integers. These powers of integers, and we have 2 sets, 2 subsets, A star and B star, somewhat related to A and B, and we know 2 things. The density of A star and the density of B star are both alpha, and moreover, we have a very strict bound that it's everywhere very close to alpha. You can see this strict bound. It says that in every sufficiently large cube, the density in the cube is some power of the side length of the cube. And it turns out that this is enough. So it turns out that we know this from step 1, that this is the setting, and Lackovich proves that this is actually enough to prove that there is a bijection from the set A star to the set B star with the property that it moves every point only by a fixed constant c, maybe a million. The important thing here is that this constant doesn't depend on A star and B star. It only depends on the parameters, which are all the same in all the continuum many connected components. Okay. Yes, he checks holds condition, that holds condition holds in every relevant bipartite graph. Now, what do we have to do to change this to, let's say, a measurable proof? Well, the issues are not very important, of course. Let me just point out that there's no expansion property here, but in some sense there is still some expansion property, which I'm not going to in details. And somehow we also define a local algorithm instead of, and then build up the matchings and take a sequence of matchings which will converge to a perfect matching. Okay, now I will talk even less about the Borel circle squaring. I will only tell you the setting of the Borel circle squaring. So this is the result of Marx and Unger. So they don't take matchings. They replace, they use flows. Okay, so what's the setting for flows in their setting? So they consider the same graphs as we consider. And instead of just having one source and one sink, somehow you imagine that all the set A is a source and all the set B is the sink. And you have to find a flow which connects the set A to the set B. The graph is the same, so we have the torus, okay, and 2 points are connected by an edge if and only if the difference is some small linear combination of some random vectors. By the way, so both our proof, both Marx and Unger proof, heavily relies on Lackovich's argument about discrepancy. So that's why it really starts with the same way. And first they prove that there is a bounded Borel F flow with this source and sink A and B. Okay, we can forget about rules. I can tell you what it means for equidecomposition. What it means that at this step, they already know, let's look at the last 2 lines there, that the characteristic function of the set A can be written as a sum of bounded Borel functions in a way that if you translate these bounded Borel functions, so translate the function gi by some ti, and you sum it up, you get the characteristic function of the set B. And what are the next step? Well, the next step is to replace a flow by an integer flow. It's some argument. And the third step is to realize that your integer flow can be replaced by I don't know, a 0, 1, or -1, 0, +1 valued flow, which is nothing else but a Borel equidecomposition of the set A to the set B. Now, I won't tell you anything about the proof. It uses some theory about hyperfinite Borel equivalence relations. The important point is that their paper is really nice and is very readable, so anyone interested should read their paper. Okay, let me finish this topic with my favorite open question in this area, and that's simply, instead of Borel pieces, can you use Jordan measurable pieces? Now, Jordan measurable is basically the same as saying that its characteristic function is Riemann integrable. And why I like this is, although I said that if the sets are measurable, then you can draw a picture, actually I think what you can really draw a picture of is Jordan measurable sets. Okay, so this is not known. Right, now, I added a new title page just to emphasize that this is a completely different topic, and you can forget everything about equidecompositions. You can forget Banach-Tarski products. Yes, that's the right thing. Okay, so I will talk about this topic of point configurations and fractal sets. It's a really large topic, and I will only talk about a very small area. And mostly, I will be interested in different. If you have a large set, you look at 3 points, they form certain angle, and what kind of angles can be formed by a set that is sufficiently large. Okay, this talk will be very much about dimensions, so I thought I define dimension. So now, here's the definition of Minkowski Box Dimension. That's very easy to comprehend. If you have a set E in RD, then you just consider the grid of cubes, let's say the grid of cubes of side length 1 over n, and then you just count the number of grid cubes that intersect the set E. Let's call that Sn, and take its logarithm, divide by log n, take the limit. If this converges, that's the Minkowski dimension. If it doesn't converge, just take lim super lim for. So this is a nice definition because it's also computationally easy to approximate. On the other hand, in theory, it's not very useful. So what mostly we use is Hausdorff-dimension. Now, I included here the definition of Hausdorff-dimensions. For those who have seen the definition but have forgotten, you can check that this is the same maybe that you've seen. For everyone else, just think about the Minkowski dimension. Okay, and what you have to know about dimension, basically it really extends classical dimensions. So if you have, I don't know, a nice two-dimensional surface, it will have dimension 2. And maybe one more example is the classical Cantor middle third Cantor set, where you start with the unit interval, remove the middle third in the 2 intervals, again remove the middle third, and so on, intersect all these. That's the Cantor set. So it's very easy to check that this set has dimension log 2 divided by log 3. Okay. Now let me give you some of the translation between. So for many problems, you can, in fractal geometry, or those problems in fractal geometry that I'm interested in, you can state it for discrete sets. So let me give you a translation on how to go from a statement about fractal sets and dimension to something discrete. So if you have a set of dimension S, that would be almost the same as if you have, let's say, in some bounded part of the space, maybe the unit ball on the unit cube, you have capital N, which is a large number, capital N to the power S points. But you have to assume that these points are well separated, so you have to assume that the minimum distance between any 2 points of this is at least 1 over n. Okay. So this is how one thinks about fractals. Now, often this is not good enough because this is something like Minkowski dimension only, and there's a more precise translation that requires more quantifiers, and they are not needed in this talk. Okay, so questions about angles. So Tamás Keleti, I think he initiated some research about angles formed by fractal sets. Okay, so let E be any set in Rd, maybe a finite set or something more complicated, an infinite set or a fractal set of certain dimension. And let's define the set of angles. It's nothing else but all the angles that appear, that are determined by some 3 points in your set. It's going to be a subset of the interval from 0 to 180 degrees. And there are many possible questions. Most of them are open. That type of questions we were interested in. Fix some angle, fix some value alpha, and what dimension of the set E guarantees that the set E contains 3 points forming an angle alpha, or what dimension the set E should have, so that we necessarily have an angle which is delta close to alpha. Not necessarily exactly alpha, we are happy if it's close to alpha. Or you can also ask about the size of the set of angles. Now, everyone who does fractal geometry would immediately see, which I didn't include here, but before you start working on angle sets, you work with the sets of distances. So instead of looking for angles, you just look at the distances formed by sets. There is this finite problem on the distinct distances problem of Erdős that is now solved, and there is this something called the distance set conjecture, the distance set problem by Falconer that is unsolved. Let's just forget those difficult problems and look at these other difficult problems when there's still something to say easily, right, or not so easily. Now, I would like to start with the second type of question, just because that's the one I can translate into a finite problem. Exact angle, the first type of question cannot really state it as for finite sets, right? I mean, large finite sets rarely contain an angle exactly alpha. But they might contain an angle which is close to alpha. It turns out that when we can meaningfully say something is that if you look at this problem and D is really huge. Okay, so actually we sort of think of that D, the ambient space, has a dimension tending to infinity. Okay, and here's the statement. So it's a weak result, but I cannot do anything better. For every positive epsilon, I would like to know what dimension of the set E guarantees that the set of angles is epsilon dense in the interval from 0 to 180 degrees. Okay. So I would like to guarantee that close to any alpha, in epsilon close to any alpha, you can actually find an angle in the set. And it turns out that it's linear in D, so there exists some constant less than 1, obviously, such that if your compact set has dimension at least this constant times D, then the set of angles formed is epsilon dense. So the way this constant depends on epsilon is written over there. I think some people here already know what results to use just based on looking this formula. But first, let me translate this problem into a finite problem. So let now F be, again, a set of 1 over n separated points in the unit ball of size of the right size, so capital N to the power C epsilon times D. Then the claim is that the set of angles is epsilon dense from 0 to 180 degrees. Now, I cannot prove one statement from the another, but their proofs is almost the same. It's just I have to copy a discrete proof and the other some other thing. Okay, now. I will tell you something about the proof of this statement. Actually, I could tell you the proof, but then I'm worried that, well, I will lose not just 80, but 90% of you, I mean, your interest, and I might run out of time. So what this theorem means, the setting is that because we have many points, obviously it cannot happen that we have all the points on a surface of dimension less than this constant times d. Now, if you work on this a little bit, what you can get is actually, you can get that there is a point, or there are actually many points in your set F, such that somehow through every plane going through X of certain dimension, you will find a very close point of F. Okay? And I've just finished the proof by saying that what you actually have to use is measure concentration property. So there's a theorem by Millman about concentration of one Lipschitz functions that can be used. It's just concentration of measurable sphere, basically. And that proves that somehow, that finishes the proof. Instead, let me tell you the other kind of problem. So this is just an upper bound. So we know it's constant times d works, but do we really need constant times d dimension to guarantee that our set of angles is dense? And the answer is yes, and this was proved earlier by Viktor Harangi. So here is his result. He proved that for every epsilon, there is a nice set, compact set, actually it's a self-similar set, of constant times d dimension. Epsilon is a constant too, so it's constant times d dimension, such that all the angles determined by some 3 points in the set is in the epsilon neighborhood of these 5 specific angles. So obviously they cannot be epsilon dense because they are very close to these 5 angles. Now, so what's the idea of the proof? Okay, so first just imagine the regular simplex in Rd. It has d plus 1 points. And one can notice that all the angles formed by these points are exactly one of these angles, 0, 60, 90, 120, or 180. It's enough to check this claim only in 3 dimensions, obvious. Now, this is not yet good enough, but there's a result by Erdős and Füredi and a generalization by Johnson and Linden-Strauss that actually you can find exponentially many points that form almost like a regular simplex. Right? So you can find exponentially many points such that the distance between any 2 of them is between 1 and 1 plus epsilon. Now, if the distance is between 1 and 1 plus epsilon, one can check that actually all the angles formed are in the epsilon neighborhood of these previous angles, previous numbers, 0, 60, 90, 120, and so on. And that's already good enough. So the way you can actually build up this set is you have this finite set F and just replace every point by a small scaled version of this set. If you want to write it down algebraically, there it is. If you are interested in the finite problem, just stop after adding it finitely many times. If you're interested in the self-similar set, just take the infinite sum. It gives you a nice compact set of the right dimension. Now, what happens? So these were the problems that were meaningful for finite sets. Now, let me just talk about a little bit what happens when you are really interested about an exact angle. This will be more algebraic. Okay, so with those group of 7 people, we proved that if you have a set E that has, if you have a set E in D dimension and its dimension is more than a ceiling function of D over 2, then it contains 3 points forming the right angle. And I proved that this is almost sharp, by proving that actually you can always find a set of dimension d½ that doesn't contain 3 points forming the right angle. So when these, even the two statements mean that altogether they are sharp, it's exactly d½ dimension that you need to guarantee a right angle, 90 degrees. And I would like to tell you why it's d½ or why my construction gives d½ I won't prove the first theorem. I will tell you something about the second theorem. So how to construct something that has that dimension and it doesn't contain 3 points. Okay, so what happens here is that if you have 3 points x, y, z, they form the right angle if and only if that scalar product is 0. Now that scalar product, if you look at it, is actually a polynomial in maybe 3D variables. The important thing, it has degree 2. And this degree 2 is what appears in d divided by 2. So the actual general theorem is that you can replace right angle by any point configuration that can be similarly defined by some polynomial, multivariate polynomial of degree, let's say r. You have to assume that the coefficients are rationals. And then there actually is a compact set E of dimension d divided by r that doesn't contain this given point configuration. Let me just give another example how this works. Here's the theorem again. So let's just prove this statement. For every angle alpha, there is a compact set actually I won't prove it, of dimension d divided by 8 that doesn't contain 3 points forming the angle alpha. Okay, so what's your task? Your task is just to come up with a polynomial of rational coefficients of degree at most 8 that somehow excludes the possibility of having an angle alpha. Okay, so angle alpha, then you have this equation for the scalar product. It's not yet a polynomial, of course. If you square it, then the right-hand side becomes a polynomial too, and you have this polynomial. But this has rational coefficients only if the square of the cosine of alpha is rational. Anyway, if the square of the cosine of alpha is rational, it works. It's a polynomial of degree 4. It actually gives you a compact set of dimension d divided by 4 that doesn't contain 3 points forming the angle alpha. Now, I could tell you, but I would rather leave this as a puzzle exercise to prove. You can use my theorem as a black box. You have to find a polynomial that has rational coefficients and works even if cosine square is not rational. Okay. I will tell you something about the proof. The proof is actually, the type of sets used are very simple. So they are just grid-like constructions. What do I mean by grid-like constructions? You start with some rectangular grid of maybe certain disks or balls, and just you have the way you obtain fractal sets. You just inside every little ball, just do the same. Just find another much finer grid of little balls and so on. Replace all these balls with much finer balls and so on. This is the type of thing that works. You have to play a bit with translating these grids, as you can see in this picture. Now, why does it work and why it's only the degree of the polynomial counts? So that's very simple to explain. It just goes back to this trivial thing that if you take an arithmetic progression is like a grid. If you take an arithmetic progression, let's say it could contain 0 as well, and if you add this together as many times as you wish, it's still an arithmetic progression of roughly the same size, constant times n. That's happens when you have many variables in your polynomial or many terms. On the other hand, the degree counts because if you multiply these sets together, if you form all these products, then you can still cover that by an arithmetic progression, but it will be a much dense, much finer arithmetic progression of size n to the power r. Somehow that's where this dependence on the degree of the polynomial count. Okay. There are a huge literature about configurations and fractal sets, and I haven't talked about it's very useful technique is to use Fourier transform and then do some estimates about dimension of sets. If somebody is interested about that, you should start with Alex Joshevich's papers. Okay. Let me briefly tell you about 2 different topics. I have no results in these, but these are some of my favorite problems. Okay. So semi-Destructor theorem was mentioned here already, at least twice, maybe 1 or 4 times. It states that if you have, okay, so you can, forget about angles, different topic, point lines, incidences, we are in the plane. So if you have n points and m lines in the plane, there is a bound on the number of incidences, so how many times can you have a point on a line, and it's roughly n to the power 2/3 times m to the power 2/3 plus something in uninteresting cases. And you can ask the same for not just finite sets, but for fractal sets. So what's the setting here? Then I have a point set of dimension alpha, and I also have a set of lines, let's say of dimension beta. It's best to assume it's not too large, maybe at most 1. So what do I mean by the dimension of set of lines? Well, by point line duality, or by some other way, you can code your lines by points in the plane and just take the dimension of the codes, for example. And the question is, how large can be the dimension of the incidences? So what is an incidence? Here you can code the incidences maybe by a set in R3 or R4, depending how you code it, and just about the dimension of that. Now, there is an obvious analog of the bound in the first theorem and here. So the obvious conjecture is that this is the maximum of alpha plus beta times 2/3, and the uninteresting case is alpha and beta. It's unknown whether it's true or not. So this basically comes from the Fürstenberg set conjecture, which I think Thomas Wolff came up with it. He named it after a very similar problem of Fürstenberg. Okay, so here the setting is maybe easier. It's very closely related to Kakaya sets in the plane, except that Kakaya sets in the plane are well understood, and this is not well understood. So we have a compact set in the plane with the property that in every direction, you can find a line that goes in that direction and intersects the set in a large set, intersects the set E in a set of dimension, let's say 1/2. And then the claim is that your planar set A should have dimension at least 5/4. The question is why 5/4? So this is the reasonable conjecture from the semi-Destructor theorem, which is sharp, by the way. So let me try and understand in this way. A line in every direction is something like having capital N lines. Now, how many incidences do we have? For each line, its dimension 1/2. You have to take the 1/2 power of n, so it's n to the power 3 divided by 2. And then if you check what semi-Destructor gives, it gives you that the set of points has to be at least n to the power 5/4. And in many settings, this calculation can be made precise, so this makes sense. This is how you calculate with dimension as well, except it's not a proof. Okay, and there are examples of sets E that have dimension 5/4. So it's known that's the proper upper bound. And the reason for that, again, we don't know anything new apart from what we know about the finite case. So in the finite case, I only know maybe 2 constructions that show that semi-Destructor is sharp, and both use some rectangular grid. And these fractal sets that E that has dimension 5/4, again, it's somehow you have a grid-like construction. Okay, so why? This is an analog of the discrete question, which is well understood, but this continuous question is not well understood. We know something less, and we know that such set E has to have dimension at least 1. This is Wolff's result. Why is that? And the reason is basically, so the semi-Destructor theorem has short, nice proofs. But there are some trivial proofs which show something less, namely these two bounds. And to get these two bounds, you just have to do some trivial double counting, and you only consider points that are far away. And these proofs can be copied to the fractal setting, and they give exactly this bound. Both bounds give the same bound here, that the set E must have dimension 1. So what's the problem with the other proofs of the real proof of the Semmelweis-Trotter theorem? And the problem is that those proofs consider not just points that are far away, but the local structure as well. And if you take a fractal set, and so let's think about the crossing lemma, or crossing number inequality proof of the Semmelweis-Trotter. If you do the discretization of the fractal set, the problem is that you will get a graph, a finite graph, but you will have many parallel edges. And although yesterday you heard a new statement about that multiplicity doesn't matter in the crossing number inequality, unfortunately that theorem has some conditions which are not met by any graphs I can define here. Okay, so unfortunately here the finite methods doesn't seem to be the right one, or doesn't seem to be strong enough. I'm not sure which one to use to solve this fractal setting. Maybe it's not even, maybe the conjecture is false, of course. When someone writes that, I will never mean that Wolf thought the conjecture is true. I mean, it's not possible. Okay, something is true, something better than one is true, and that U2, Katzenthau, and Burken, they can prove that such set E must have dimension at least 1 plus epsilon, when epsilon is some fixed absolute constant, positive constant. Now these kind of proofs, and this proof relies on additive number theory, so Pollock-Semmelweis-Covers theorem and Plünecker-Ruzsa inequalities. It's a nice one, but it won't give anything close to the true conjecture if it's true, or maybe it's not true. Okay, so let me finish with another open question. Actually, this is, I will call it the 3-segment problem, but I'm not going to tell you why it is called the 3-segment problem. If you want to know that, you have to read that paper. I wrote the title there. Let me attribute this problem to Lackovic and Pósa. Lackovic would attribute it to Pósa, I think. So this is the new problem appearing in the title of the paper, but this new problem is already 25 years old. So the setting is very simple. Take 3 measurable functions. So from the reals to the reals, measurable functions, and then just imagine the graphs as a subset of the plane. Obviously, every vertical line will intersect all the 3 graphs. The question is, can we always find a non-vertical line that intersects all the 3 graphs? And this is unknown. Also unknown with 4 functions. I can solve it with 2 functions, but not with 3 or more. It has many almost equivalent formulations, not just the 3-segment problem, but some other ones. I will mention one which is, well, here is one which is about fractal geometry. It talks about irregular 1 set, so a set that has dimension 1, positive measure, no rectifiable part. Then the statement or the conjecture says E should have 3 collinear points. But instead of finishing with this one, let me finish with a finite problem, which might or might not be related. It's related, but might not be closely related. So it's possible that one can solve this question without solving the Lackovic-Pósa question, or the other way around. So just consider the n times n grid of squares, and choose constant times n little squares for some constant c. The question is, can you always find a line that goes through 3 squares at least? Of course, when the constant c is 3, I know the answer. For smaller constants, it's more interesting. And the question doesn't end here. Of course, you could instead of 3, you could ask it for 4 squares or 5 squares or something even that tends to infinity as n tends to infinity. All these are open questions. So I would be very interested in all these possible answers. So thank you very much.
What happens if F1, F2, and F3 are continuous?
Yes, I was planning to mention that. If continuous, then start with a vertical line and just move it a little bit, it would still intersect all the 3 graphs. So they shouldn't be continuous.